Yeah, so my name is Radek, and I will guide you through the journey of the internals of fate. Let's start with some agenda, as usual. So we're going to start with a little bit of history, some origin, motivations for fate. Then we are going to see what is the data that's processed during the runtime. We'll take a look into some assembly code. We'll learn about what is the theoretical model of the execution, what's the overall schema of things moving around. I'll briefly talk about how gas is calculated, and in the end I'll show you a little bit of live example, let's say. But first, please let me reserve one slide about myself. So my actual name is Radoslaw Rowicki. I come from Poland, where I finished my education. I became a so-called master of computer science. I wrote my thesis about Sophia. At Eternity, I'm mostly responsible for the compiler of Sophia, for developing the language, and for fate. So, what is fate, first of all? Well, it's an acronym. It stands for Fast Æternity Transaction Engine. But for the purpose of this presentation, let's call it a freaking awesome transaction engine, because we're going to discover that it's not actually about being fast. Technically speaking, it's a stack and register based machine, which means that it shares some memory designs from CPUs that run on our computers. It has been specifically designed for Eternity blockchain, so it's like our own internal tool. You want to rather see it anywhere else. And it's a part of the core node. It's written in Erlang, so if you want to look it up, you need to navigate to the main repository on the AE-Fate app. So, a question my imaginary friends tend to ask me very frequently is, why a custom VM? Why this idea in the first place? Why not EVM, which already exists and it's there? Well, EVM has its own flaws, which we wanted to address. For example, re-entrancy. It's something that we don't really like, and people lost quite substantial amounts of money on that. Bugs are extremely harmful on blockchains, because essentially once you deploy something, it's too late, you can't fix it, and buggy code operates on your money, so we wanted to address that by having a machine that at least to some extent aids you with ensuring that code is more likely to be correct than wrong. Chain storage is a very valuable resource, as we see it on Ethereum. The gas prices are pretty high, and the chains can get easily clogged by the amount of data that's stored in block. There are some just limitations, so this is something we addressed as well. Next thing is that validation of code. It's pretty hard to do on compiled contracts, and our assembly is sort of different than EVM, for example, as we are going to see later. And simply by making our own implementation, it is just easier to adjust it for our needs. So when suddenly we want to have native supports for, zero knowledge proofs, we can add some cache functions, and we don't have to ask anybody about it. Aside from, of course, community accepting the fork. And also, hypertext support, which wouldn't make sense on EVM. Yeah. So, well, what are the key features that make Fate special? First of all, the most advertised one is tape safety, which means that whenever you make a call to a smart contract, the data is being checked right away. So it's impossible to launch an entry point with wrong data, with data that doesn't make sense to be executed. Re-entrancy is absolutely banned. You can't just do it. And we know some stories from Ethereum, where it cost many people to lose lots of money. So, well, if you don't know what reentrancy is, this is the case where one contract calls another one, and another one calls ours back, possibly in some invalid intermediate state. So at Æternity, we don't have this issue because of that. We have safe arithmetics, so integers, this essentially means that integers do not overflow nor underflow, they just grow as big as you wish. Of course, at certain gas cost, but you won't have like suddenly integers rolling to negative values despite being clearly positive. Fate supports many operations on data structures as primitives. So instead of having to implement every single thing in Sophia or Fate itself, we have native support for stuff like maps, lists, tuples, etc. The assembly code is readable. It's not, of course, perfect. It's not a natural language, but it's something that is actually auditable if you really need to take a look into it. And, of course, it features some Æternity primitives, such as oracles, AENS, but essentially whatever you can do at Æternity, you can do it through Fate. So, well, execution is about data processing. Execution rarely makes any sense when there's no data to be modified, processed, moved around. So let's start with what data looks like and what data kinds do we have. We have unbounded integers as promised, so this means basically numbers. We have booleans, which are different than integers. So you can't write something like if 3, then do something. What does it mean? And there are strings. They support Unicode, which is pretty nice. They are lists. These are not like arrays you know from languages like C. These are like more functional lists, let's say, also called stacks, like with head and tail pattern. You might have met those. And there are hash tables, which are built in. This is not a feature on EVM. And yeah, I said blockchain primitives, for example, oracles is just an item on the blockchain. There are some arrays, but like bit and byte arrays that are used to represent data. For example, hashes or serialized information. And last but not least, tuples and unions, if you have PhD, products and co-products. So, if you have some experience with Sophia, you might see that most of the Sophia types are clearly like one-to-one to their things listed here. Two things that are missing though from Sophia are custom data types, for example, like this data type thing or records. So in Fate, this looks slightly different. And let's take a look at some Sophia code and its representation in Fate. Let's start with records. So here we see some record with two fields. One is an integer and one is a string. Yeah, it's a data structure that holds some sub-data under named fields and some example value below it. So this essentially compiles to a tuple under Fate. It's just a tuple. What's important to know is that all information about names of fields is entirely lost. So yeah, something to keep in mind. A caveat to that is when you have a record with just one field, this compiles instead of to a tuple, just to the underlying value. So if you make records like that, there's absolutely zero overhead on that. And this has some nice use cases. For example, you can name your type in a different way in Sophia. For example, to distinguish IDs from token values, which both are integers. Regarding the data type construction, which is technically an algebraic data type, also variant type or type union, depending on where you come from. There's a special type union construction in Fate that is used to represent that. So essentially a type is just told to be a variant type with a list of constructors, and each constructor is a list of types that parameterize that thing. So for example, here we can see that I have some laser pointer. So here we see that we have some variant value of I2, which carries 2 integers, and that is compiled to a structure that holds those 2 integers, and the 0 means that it's the constructor number 0. So again, constructor names are lost during the execution, during the compilation. So let's take a look at some assembly code. Here is some prominent school example of a function that calculates factorial. Essentially, it means, this is Sophia code if you're not familiar with that. So essentially, this is the name of the function, this is the argument, and the algorithm is simple, like if the argument is lesser than 2, then we return 1, and if it's not, then we recursively calculate factorial for the lower number and multiply it by the argument. Definition of factorial, essentially. So how it looks in Fate. This is the assembly code. It might not be the most beautiful code you saw in your life, but you really don't have to be a member of Mensa to make some sense from it. Yeah, we can see that it declares a function that takes an integer and returns an integer, so it's typed already. And yeah, it performs some comparison between the argument and the number 2. Yeah, this is what we saw in the previous, so this is this place. And makes a conditional jump on the result of this operator to block number 3, which returns 1. So I know it's not entirely clear if you don't have any experience with that, but what I'm showing right now is that, well, it is possible to read. It is readable. And to look at what it looks at EVM, for example, for the very same function compiled, I think you can expect what you're going to see by the amount of space I left for that. It looks like this. It's the same function on Ethereum, and this is Fate. So if I told you that there's a bug on the version on the right, would you be able to find it? Because I wouldn't. To me, it's just too cryptic and too big and incomprehensible, while the code on the left is very concise. And this is what I meant by auditable and readable code. Well, it's not that EVM design is fundamentally bad, don't get me wrong, because, for example, yeah, it's just a different approach. It's much more verbose, so it's possibly easier to JIT compile. There are JIT compilers for EVM code, but it depends on our priorities. And at Æternity, we went for clearness, saving space, and being able to, I don't know, at least to some extent, reason about what we produce. So another difference that you might have noticed is that EVM code is almost entirely flat. There are some tags in between instructions, but in Fate, there's a little bit more structure. And let's take a look at it. So each contract consists of functions, and each function consists of blocks. What makes it special is that you can't perform a jump to a middle of the block. You always jump to the beginning of the block, which already helps making some sense from the assembly code. And each block consists of a special block ending instruction, for example, making a call or returning or jumping to another block. More than that, you can't just jump from one function to another one, like you can do in Solidity and EVM. So what instructions are there supported? Well, there are some arithmetics, so like addition, multiplication, taking to the power lesser than comparison, which compares numbers. Some memory management. So for example, we can push items to accumulator stack, we can pop from it, we can store to the memory. There's some, of course, control flow, so jumps, we can call functions, and these are primitive instructions in there. There's data manipulation, so we can create tuples, we can query tuples, build data essentially, and deconstruct it. There's blockchain interaction, so we can perform from Fate directly spend transactions, we can create new contracts in a single instruction, and interact with features such as AENS, oracles, and whatever. And there's some cryptography also built in for performance reasons and convenience as well. So you don't have to rewrite all the cryptography in Sophia. You just have it in there. So let's take a look at the execution schema. What's supposed to be? Okay, so while Fate executes, it needs to have, it carries some memory, it carries some values on its way. So first of all, while executing a smart contract, the whole blockchain state must be known because, well, we have to perform spend transactions, for example, and we need to interact with the blockchain. So we need to know what happens at the blockchain. So this is contained in Fate memory. We, of course, need to know what's the code of the currently executed contract, where we are in that contract, how much gas is left, so we can terminate the execution when it's depleted. And there's some memory, of course, like computational memory, which consists of execution stack. It's a stack on which we push return addresses. So when we return from a function, we know where to start over. And it's a separate stack from accumulator stack. So when we compute intermediate results of some complex operations, this lands on a separate stack, so you can't overwrite your return address like you sometimes do in C. There are some variables registered for quick access, so if you create I don't know, you can always quickly access arguments of a function without having to dig deep into the stack. And there are some structures used for optimizing maps because, well, node is written in Erlang. Maps are immutable, which renders them slightly inefficient, and we took measures to counter that issue with some specialized data structures that are actually mutable. So, execution model can be described using this simple state automaton, and yeah, so every execution begins with some initialization. The machine then picks the first block, which is evaluated by picking an instruction, evaluating the instruction. An evaluation of instruction can result in either, well, continuing within that block, jumping to a new block and picking it again, or terminating it for either success, terminating the execution either with success or failure. Let's quickly take a look at gas calculation. It's going to be a brief overview because, well, this is quite complex and it deserves its own lecture, to be honest. So what do we pay for? You pay for each instruction. Every instruction has its fixed cost, and the list of that can be seen in the protocol repository of Æternity. Some instructions, such as calculating, I don't know, powers or lengths of stuff, have additional cost that is linear to the size because we have complex operations as primitives, which can vary depending on the size of the data, so you pay for that as well. You pay for allocating memory. We'll briefly see how it works. And for serialization of data. So when your contract terminates, the stuff needs to be written down to the blockchain, and that is charged as well. So to give you some, like, I don't know, brief view on how particular instructions cost, simple operations take usually like from 100 to, from 10 to 100 gas. These are like addition and division and basic stuff like that. If you make a query to the chain, it's usually like 100. Write chain operations are very expensive because they need to alter the state trees. Cryptographic operations, whatever they are complex, so it's something to keep in mind to check if you're not abusing it. There's a no operation, which does literally nothing by its definition and costs 1 gas, and I find it cute. And some big operations, they of course charge depending on the size of the data. For allocating memory, the algorithm is a little bit peculiar. So one cell is considered 8 bytes of allocated memory, and the price for allocating memory is charged by cell, and the price is progressive, just like taxes in some countries. So for some range you pay 1, and then you pay 2, and then you pay 4. So like for 2,137 cells you would pay 3,339 gas, according to the formula. Regarding serialization, essentially you pay for traversal over the data and serializing it, so primitive data is charged 1 gas per byte, and for complex data per each node in the definition tree, because data forms 3 nanocycles in fate. So let's conclude it by showing you some practical live example, because you have seen some theory, so how it looks in real life. Let's get back to the factorial function. I hope you're already a little bit familiar with that. And let's take a look at the assembly again. So here, can you see it? Here we have memory, which stores the argument. Here we'll have an accumulator stack. Here we have the execution stack where we will throw all those return addresses, and the frame tells us where we are and what's going on. So we are executing the FAC function of type from integer to integer, and we start by picking up the first instruction, which is comparison of the argument 0 against the number 2. And this A means that the result has to go to the accumulator stack. So, well, 4 is clearly not smaller than 2. So we put false on the stack. Then we proceed to the conditional jump, which essentially takes value from the accumulator stack. And if it is true, then it jumps to the block numbered by the last argument. And if it's not, the execution just proceeds. It's worth noting that each read from the accumulator stack pops from it, so the value gets used, and since it was false, we just proceed. Next is the subtraction, so this is the point where we calculate n minus 1. So argument 0, which is 4, minus 1 is 3, the result gets pushed to the accumulator stack, and we call recursively FAC function again. And what happens right now with the call? Well, first of all, we need to create an execution stack frame, which will make a snapshot of the memory at the current state, and the return address, so we know where to proceed after this function is finished. Arguments to functions are taken from the stack, so from the accumulator stack. So this 3 gets to the memory to replace the argument, yeah. And we perform the call by jumping to the location. And the whole operation is executed again, because, yeah. So we perform the comparison, 3 is not lesser than 2. We perform conditional jump by not performing it, because it's false on the accumulator stack. So we compute 3 minus 1, which is 2. And again, we make a snapshot on the memory, we record the return address, push it to the execution stack, we update the argument, and round robin again. So again, 2 is not lesser than 2. We don't jump, we calculate 2 minus 1. We call to the factorial again by creating an execution stack frame. And now things are going to change, because 1 is clearly lesser than 2. So we put true on the accumulator stack this time. The conditional jump now triggers. So we jump to block number 3, yeah, because this was the 3, and the operation is to return. And return 1 essentially pushes this 1 to the stack and performs the return operation. So what does it look like? First of all, we need to bring back the memory from the top of the execution stack. Yeah. Then we update our location using the return address. So here we are. And now we can safely pop from the execution stack the last frame because we don't need it anymore. So we are again here at the multiplication point, not again for the first time actually, but so yeah, we multiply the argument by the content of the stack, so 2 times 1 is, well, 2, and we return. Again, we bring back the memory from the snapshot, we update our position according to the return address, we pop from the execution stack, and then we proceed again. So 2 times 3 is 6. The result lands on the execution stack again. And we do the same thing one more time. So we bring back the memory, we bring back the position, and pop from the execution stack. We perform the multiplication, we are at this instruction again, and now we return. So what happens now? Because normally we used to bring stuff back from the execution stack, but since it's empty, that means that the execution is complete. So we just terminate the execution, and we are happy with our result, which is hopefully correct, isn't it? And that would be it for this presentation. Let's maybe get some conclusions. So what I would like to remember from it is, well, Fate is the smart contract runtime system for Æternity blockchain. It mainly aims for expressiveness and safety, and also size of the code. It is an inherent part of the blockchain, so yeah, whenever you write a smart contract in Sophia, your contract will be run on Fate. So in my opinion, at least, it's worth to having a little clue on how it works and what's going on there and what to expect from it. Thank you for your attention. It was a pleasure talking to you. I hope you understood something.